Okay, so I think we're live streaming now. So I'll start with a screen share and see where we left off last time. And so I wanted to talk, I think we were right here last time. We had talked very briefly about systems, internal forces, external forces, etc. So I know we had ended with that, but I don't think we had done any problems at all with it. And so before we get into doing actual complicated calculations, let's again, this is on page 91 in the workbook. So you've got this information here. You can read it a little bit if you need to kind of review, but I wanted to start here at 5.25 and let's just go through it together. We're not actually trying to do any FBDs or anything. We're just trying to identify what is an internal force, etc. And so if you want to try and do this, just pretend it's like a little quiz. We could do it together. Yeah, let's just see if we remember anything before we go on and do the next problem for real. Okay, so 5.25, we've got this figure. We've got a bunch of different blocks here. It's really complicated looking. There's going to be a pulley system in there, and we're told that friction prevents block 1 from sliding relative to block 2. So I know we haven't discussed too much with friction yet, but basically friction is what's holding block 1 on top of that big block number 2. Great. Now there's going to be several interesting choices for systems. There's 5 different blocks. You could do a block 1, 2, 3 system. You could do a block 4, 5 system. You could do a block 1, 2, 3, 4, 5 system. You could do a block 5, 3 system, but that's not really a good choice because it's, yeah, anyways, let me leave it like this. Let's just focus on the 1, 2, 3 and the 4, 5 at first. So in part A, it says, what forces are internal to the block 4, 5 system? Okay, so zooming in here a little bit. There's the picture. We've got blocks 4 and 5. And so let's say we make blocks 4 and 5 our system. So that's my system. And I'll just say it's the 4, 5 system. Okay, what force is internal to that system? And you can unmute anytime you want here.
Is it the natural force?
Okay, and I call it the normal force, natural force.
Yeah.
I know what you mean. So excellent, right? There's a force up. I would call this, say, N45, but there's the same force magnitude down, N54. That's nice. So that is the force that is between these two. By the way, this is kind of foreshadowing the next problem. I want to point out that the N45 is equal and opposite to N54 by Newton's third law. Whoops, sorry. But N45 magnitude is equal to N454, excuse me. So be aware of this. You're going to notice this happening a lot in the next few problems. What happens is sometimes I get really lazy and I just start writing 4, 5 on everything, or 1, 2 on everything, or 3, 2. And sometimes I'll switch them back and forth. The reason I can do that is because the magnitudes truly are interchangeable, and we've accounted for the directions with the arrows. All right, that was cool. All right. So let's say we make, in part B, it says, imagine this big thing up here is our system now. Okay, so if blocks 1, 2, and 3 are the system, somebody give me an internal force, somebody else.
Normal force as well.
Which one?
Well, there's one from 1 to 2, and then
Okay.
2 to 1.
All right. And so if I just call this N12 and N12, if I call them both N12, is everybody okay with that? Because they have the same magnitude and I drew the directions opposite. So for me, in my notes, N12 is basically the normal force that involves blocks 1 and 2. Nice. That's good. Is there another one?
I have a question.
Oh, go ahead. Yeah.
So how come it isn't N21 when the force is going up? Or
Do you
pushing
agree?
up?
It doesn't matter at all because I could say this is also equal to N21, right? That's what I'm trying
All
to.
right. Okay.
And so that's what I'm saying is now that we know the magnitudes are equal, I'm just going to start getting lazy. Is that cool?
Yeah, I get it.
It's not technically illegal to do that mathematically since the magnitudes are the same. And that just saves time in the notes, basically. All right. But you're absolutely right. It should have been 2-1, but yeah, mathematically it's the same. Good question. Do you have another internal force for me or no?
Would there be a friction force between 2 and 3?
Let's see. Between 2 and 3, there's not a frictional force. What type of force is 2 exerting on 3? That was a good thought.
Tension? No, not tension. Let me see.
There is a force between them. It's at this interface. What's the name for forces at the interface that push perpendicular?
Normal?
Normal. Excellent. So you're right. There's a force between 2 and 3, but the idea is friction would be up and down on that surface, right? Friction, we haven't really talked a lot about friction, but friction is usually parallel to the surface, right? If you rub your hands together, the friction is parallel to your hands. Or if I'm dragging my hand across here, as I drag my hand across, friction is trying to hold me back. Well, I'm moving this way, so friction is that way. Friction tends to oppose motion, and motion is generally parallel to surfaces. Not always, but you know. So that was a great thought. This was from last night. Sorry. All right. Yeah, that was a good thought. So let's go back into there. So I think what we did is we said there's a normal force here and there's a normal force there. To keep track of it, I'll call this one 2, 3 because it relates to blocks 2 and 3. And we know that the order of the subscripts doesn't really matter. We said there was another one up here, normal force that relates to blocks 1 and 2. That's the normal force between blocks 1 and 2. There's one more internal force between the 1, 2, 3 system.
Would it be with the table?
The table. So let me see if I could draw this carefully. The table is not inside the system. So the system would just be this crap. Let me see if I can get this. I know it takes a second. So right there, what I've shown in the green circle or tried to show, notice the table is not inside the system. So that could actually be another system. You could have the 1, 2, 3 pulley 4, 5 table Earth universe system as well. You could so it turns out table is not it. The table does produce a force though. You're right. It's just not internal. Good thought. Others or any other guesses? There's one more force that's internal. It's between blocks 1 and 2.
The frictional force.
Yeah, I snuck that one in there in the problem statement. I don't know if you remember, I said there was friction between those blocks. So just for fun, which way is block 1 going to move? If we let go of this crap, do you agree that 5 is going to fall down probably? It's not going to fall upwards. So that means 2 is going to be pulled forward and 1 is sitting on top of it. Which way do you think the friction would go on block 1?
So the friction is pointing to the left?
it would actually go this way. Friction would go forwards on block 1, but it would go backwards on block 2. And the idea is block 2 is the one that's tried to move to the right. And if there was no friction, block 1 would just stay right there and fall off the back. So the friction is what pushes it forward and keeps it on top of block 2. By Newton's third law, the friction must be the other way on block 2. Isn't that crazy? It's sort of like friction is what makes you go forwards when you walk or drive your car. It's kind of weird. All right, let's I don't know, questions on that before I erase, or we'll revisit friction in the next chapter, by the way. So if you didn't understand the direction of friction, I'm going to practice that with you probably Monday or next Wednesday. That's a tricky thing. Let's see what else we got in this question. I don't know if there's anything. Ooh, can you guys think of a system where tension in the string is internal? So we're looking for a system where tension in the string. I want the tension to be internal.
Would it be between 2 and 5?
2 and 5 would work. So would 2, 3, 5. So would 2, 3, 4, 5. So would 2, 4, 5. So 1, 2, 3. Yeah. Basically, as long as blocks 2 and 5 are in the system, the tension between them would be internal. Now, I know this seems a little bit crazy, but this is kind of a look at this coordinate system you would have to use, though. You would have to say X is that way. Now, give it a second to update. X would have to be basically clockwise. And this is foreshadowing circular motion. This is how we can handle circular motion. Instead of saying X is to the right or to the left, we basically talk about a coordinate system going clockwise or counterclockwise. Isn't that kind of cool? I don't know. I hope you enjoy that. Yeah. Let's see. Let's see what else. All right. Let's see what Freddie has to say here in line D. If the friction is insufficient to keep block 1 on top 2. So imagine there's a little bit of friction, but not much. For example, imagine block 1 is actually an ice cube. You could imagine that block 1, the ice cube, you could basically pull block 2 to the right and the ice cube would fall off the back. Is it okay to still treat the friction between 1 and 2 as an action-reaction pair? Is it okay to still treat 1, 2, 3 as a system? What do you think? Any thoughts? So again, suppose friction is insufficient to keep block 1 on top of block 2. Freddie says it's okay to treat 1, 2, 3 as a system because the friction is still an action-reaction pair. What do you think? Any thoughts? Let's start with one piece of this. Is it okay to think of the friction between 1 and 2 as an action-reaction pair? So let's say block 1 is slipping off the back, right? It would tend to be moving this way. So I would call that V1 relative to 2, right? And so friction would point opposite that way. So I would say there's a friction between 1 and 2 going this way. We already discussed if 1 is falling off the back, that would cause a drag on block 2. So there'd be a friction 1, 2 this way, right? And so is it true that friction 1, 2 and friction, let's call this 2, 1 or whatever, is it true that those are still action-reaction pairs? What do you think?
Yes.
Absolutely correct. And it's like very counterintuitive. I'm trying to trick you. So then based on that, do you think it's okay to treat 1, 2, 3 as a system still? What do you think?
What makes a system?
I like that you aren't immediately responding. I'm trying to trick you and I'm not succeeding. This is good. A system is a group of objects that moves together as a group. Based off that, is it okay to call them a system?
No, because object one is moving in the opposite direction.
Yeah, nice. So just because you have action reaction pairs doesn't mean you could make a system. That's what I'm trying to. Okay, so the goal here was to learn this. Remember that there's internal forces. Internal forces are not the same thing as action reaction pairs. However, most internal forces are action reaction pairs, as we've seen. Every single one we did was an action reaction pair. But just because you have action reaction pairs doesn't mean you can legally call it a system and make it an internal force. The objects have to be moving together. And that was what I was trying to remind you of last time. And that was really all we're getting out of that. Any questions out of that? Action reaction pairs are always valid. Systems are only valid when things move together as a group. And internal forces happen to be action reaction pairs. What's up, Jay? Any thoughts you have on that? Action reaction pairs or whatever? Okay, got it. All right. Let's go on to the next question now. And let's see. Give me just a sec. Oops, let me make this a little bit smaller so I can see better. Okay. All right. And so I'm going to do this one for you or with you live. Okay. So, and then what I'm going to do is I'm going to split us into breakout groups and let you try this one. And we'll just see how this goes today. So we're looking at 5.26. All right. And sometimes it helps just to see me roll. And I think that'll be the best way to approach this. For the first problem with multiple blocks, let me just rock this out for you. Okay. At any time, if I'm rolling and not paying attention, ask Jay a question. All right. The size of the blocks doesn't really matter, but oh, I think I showed the first one is bigger. I might as well try to make it look like the picture. Okay, so we've got blocks 1 and 2. I'm going to do an FBD of 1. And I think there was a force, wasn't there? An applied force. Okay, so we got this force here. The magnitude of that force is F. All right, so if I draw a free body diagram for object 1, well, I know I have that force. What's another force? Anybody can unmute at any time. What's another force on block 1?
Normal force between 1 and 2.
Yep. So I'll just call that N12. All right. And then I guess there's going to be a weight. I'll call that M1G. And probably a normal force up. I'll call this one N1. So, whoops, there's some glare. That's a little better, I think. So the idea here is this is my standard way of doing this problem. It's not like I'm the only one that has a way to do this, but since you're working with me and all of my notes are written like this, it's probably worth mentioning a few things. Number 1, I use subscripts a lot. Number 2, the subscripts between the two blocks, it's going to be 1, 2. If you use 2, 1, we've already discussed. Who cares? 1, 2, 2, 1. Yeah, I get the idea. Notice up here, the normal force from the floor, you could say, shouldn't that be normal force 1 and floor? You're absolutely right. But I usually get lazy. And so with the floor, I only use 1 subscript. Why I do this, I don't know. It's just I got in this habit. So if you see a normal force with 2 subscripts, that's a normal force between two blocks. If you see a normal force with only one subscript, that has to do with the floor or the ramp and a single block. So that's just my style. Is it the best? No, but does it work? Sure. Also, let's not forget, when we draw a free body diagram, it's usually worth it to indicate the direction. And I'm assuming these things are going to accelerate to the right. How do I know that? In this problem, was there friction?
No.
No. So if I push something and there's no friction, isn't it going to accelerate that way? I think so. So that's why I know it's accelerated. So if you're not sure if something's accelerating, you could just say it's accelerating. That's always true. And then if you find out later it's not accelerating, you'll be like, of course, it's accelerating with rate 0. Didn't you know? And so it's always okay to put A here. Only sometimes is it okay to put 0 here. So if you're not sure, if in doubt, put an A and then read the problem carefully and dig around and see if anything says constant speed or something. All right. Am I forgetting any forces here? Let me just check the problem really quick. Okay. Got it. I think that's it. Let's look at FBD2. All right. So what are the forces acting on block 2? Give me one of them. What do you think? I'll get this one. What's another one?
Friction going to the left.
Okay, good. There would be friction going to the left. Now, in this problem, I think it said friction was negligible. So you're right that friction would normally be there. But yeah, okay.
What is the F then? Is that just force?
Oh, that's like a zombie pushing on it. So that would be me. So sometimes I'll call that the applied force. So watch out. Usually capital F will be like a zombie pushing on it or something. Whereas a lowercase f, I'm going to always use a lowercase f for all the friction in my problem. Is that cool?
Yeah.
That's my way of trying to give you that hint that this is something pushing on it rather than a friction.
So the normal.
Yeah, nice. Which normal? From the floor or from the block?
From the block.
Okay, which way is that going to push?
To the left.
So 2 is pushing to the left on 1.
Yes.
So which way does 1 push on 2?
Oh, then it pushes to the right.
Yeah. And think about it. Block 1 is slamming into block 2, which is pushing it that way. Outstanding. All right. And you could call it N2-1, but then later on in my equations, I don't want to think about it because 2 and 1, I'm just going to call them both 1-2 since they have the same magnitude, opposite direction, Newton's third law crap. Great. Okay. I think there's some other stuff on there, isn't there? Is there? What's holding this thing up?
Normal force from the table up or from the floor up.
Yep. And so what do you think I would call that? How do you think I would label it?
N2.
Absolutely. And what's the force that's pushing to the left?
That'd be N12, right? But that's on the other FBD.
That's on this one, correct? So what's the force on block 2 that's pushing it to the left? Aren't I mean, Jay?
I'm guessing nothing because it's going to be
Absolutely.
accelerating to the right. Yeah.
Yeah. So I'm trying to remind people that, hey, you don't always have to have forces in both directions. Let's see. Is this plausible? There's a force pushing it to the right and nothing holding it back. Well, it's going to accelerate. That's totally fine. Sometimes students get in this feeling that there has to be a force pointing to the right and to the left all the time. Sometimes it's just not true. And you caught the trick. Nice job. Trying to trip you up. All right. So if you want, take a second and quickly write down what you think the force equations are. Okay. Hopefully you've got that on your paper. So I'm going to write my own force equations here and then, or I don't know what the hell, let's just do it together. All right, let's have some fun here. Somebody give me a force equation in the X here. Somebody just say it to me.
F minus N12.
F minus N12. Okay. Then what? That's not an equation. That's part of an equation. You see where I'm going with that? What's the rest of it? What does it equal?
Is equal to MA.
Close. I would be a little bit more specific.
Is it M1A?
Yeah. So we have to be very careful now. When you have two blocks, F doesn't just equal MA, it's which M is accelerating in that FBD. So for this one, we have to say sum of forces equals M1A because it came from the number one FBD. All right, nice job. And then in the X direction, I'll do this one. N12 equals M2A. And so we see that, oh crap, if these blocks have different masses, that is going to actually matter. So, all right, we're building up the complexity now. Okay, so now we'll do the Y direction here. Now, I'm going to show you the Y direction myself. You guys probably know that N1 is up and M1G is down. So you might write this, N1 minus M1G equals M1. What's the acceleration up and down for this block?
0.
0. So isn't that equal to 0? It is. Now, sometimes, do you agree you could just move this over to the other side? And it would read this. Sometimes, if acceleration equals 0, I will skip to this step. And what I'll do here is, if acceleration up and down is 0, what that means is the up forces equal the down forces. So this is ups equal downs because AY equals 0. Does that make sense? You could always do you could always say N1 minus M1G equals 0 and then rearrange it. But sometimes it's just faster to do this. And so I'm just showing you that tiny little shortcut. Okay. Over here, I'm just going to skip right to it. Just saves me time in later problems, it turns out. So again, I'm saying the ups equal to downs because AY is 0. And you could do the same thing with lefts and rights if AX equals 0. So far, so good? Hope so. All right, and then what's the next part? Oh, it says do a system FBD. Remind me, when can we do a system FBD? Under what circumstances is it appropriate?
When everything moves together.
And do you agree in this case that applies?
Yeah.
So if I could do the system FBD, right? Okay, we're going to have, I'll just draw it here, just so we kind of get an idea. So there's the blocks, just kind of this big ugly block here. What's one force on the system? I know the blue one, F. What else?
The MG or negative, or yeah, MG
Yep.
and normal force.
And so, yeah, exactly. And now keep in mind, we have to be a little bit careful here. This is not the same thing as normal force 1, because now we're talking about blocks, both blocks being supported. It's not the same thing as normal force 2. So this one, when you use the system, is the one time I use the normal force without any subscripts. So this is the total normal force from the floor on the system, which in this case happens to equal N1 plus N2. Down here, should I use M1G or M2G? Both of them, right? And so M total here is just add the two masses together. What force does not appear in the system FBD? Which one doesn't show up?
The normal force between the two blocks.
Which is an internal force. Nice. All right. Now, check this out. If I do the X, Y, and it's accelerating this way, check this out. Let's write the force equation in the X direction. So in the X direction, what's the force equation? There's only one force. What's it equal to in this case?
F?
F equals what? If we're doing the horizontal forces,
M total A.
yeah. I had a little coffee today, people. I'm on my 3rd cup. I just gave up. I'm not going to sleep tonight. I'm going to party all night working on physics. All right. So check this out. It's not that bad, but you have to pay attention. 1, 2, 3, 4 different normal force possibilities here. If you don't use subscripts and keep track of them, you will screw up and lose points. That's not fun. There's different masses. You're constantly having to keep track of which mass, which normal force. And furthermore, you also have to notice that acceleration in this particular problem is all in the X. You could easily imagine another problem where there's some AX and AY, and you'd have to keep track of those as well. And so it's not that hard. It just takes practice and a lot of it and attention to detail. And I don't care what your major is, having to be organized and neat and pay attention to detail, that is going to help you succeed even if you hate physics. I mean, that's all there is to it, right? Being detail oriented is going to help you waste less time in your future job. And that's probably why a lot of people want you to do this class. All right, let's keep rocking. The Y direction, boring. Ups equal to downs. N equals M total G. All right. Any questions about that? That is 2/3 of this type of problem or more. This is what it's all about. Jay, do you have any thoughts that you'd like to share with them about your reflections or any advice or not?
Yeah, just keeping straight. If you're doing a system, make sure you do M total, because I know that definitely I have made the mistake of just choosing one mass instead of doing the total mass, and it's very, very important.
Yeah, you end up
So-
wasting a lot of time if you choose the wrong mass, right?
Exactly. And most of the time I'll actually get M total for the weight. That makes sense for me. But sometimes I'll mess it up with the mass times acceleration. So just make sure you do it for both of those, both the weight and the acceleration.
I gotcha. Yeah, gosh, I forgot about that too. Yeah, because a lot of people sometimes you think about you're accelerating, you mix up A with G because G has acceleration. Is that what? Yeah. So remember, G here is not the rate at which this thing is accelerating, but yeah, it's how fast it would accelerate if it was falling straight down, which relates to the weight. Oh man, yeah, you're right. Don't forget the G in there. Mass and weight are yeah, very good. Jay, how did you organize your papers and stuff? Did you do you have an old sample of your work that you could show them when you did some problem from chapter 6 or something?
Yeah, let me just grab it really quick.
Yeah, yeah, and then we could look at your work. So while she's doing that, we'll see if, and because obviously she did excellent on this stuff and when she was taking it, so maybe she has some wisdom to impart that I don't. All right, she knows what you're experiencing better than I do. All right, so let's look at part D while Jay's looking up that. So in part D, it says, which one of these looks like it would be the best to figure out the acceleration? So if we know the force and the masses, which one is the best choice to determine A? Is it FBD 1, 2, or 3? What do you think?
FBD 3.
Yep, right there, because we know this, it's just divide and you got it. So this is the advantage of the system FBD if you could use it. It's usually very easy to get the acceleration. Which one is the best to get the normal force between the blocks?
FBD 2.
Yeah. So notice this is a tricky, interesting thing. Oftentimes, the two best FBDs to use are the system FBD and the block that's not in contact with the zombie. So the one that's in contact with the zombie is slightly more complicated. And so it turns out, actually, when I would do this problem, sometimes I wouldn't even draw FBD 1 because the other two gets everything I could possibly hope to learn from this. Anyways, all right. And so let's pause right there. Let's see. Oh, let me ask you this. Suppose this is the force that I want to call the action. So let's say M2G is the action. All right, the force associated with it. What would be the reaction force associated with M2G? So if M2G was the action, what's the reaction? Does anybody feel brave?
N2.
Nope. Remember that normal force and weight can never be an action-reaction pair. They're different types of forces. Remember that? What type of force is this? Focus not on the direction, but the type of force.
Gravity?
It's a gravitational force. Okay, so we know it's a gravitational force. What are the two objects involved? Right? You need two objects for a force. So one of them is the block 2. What's the other object that causes that gravitational force?
Would it be the mass of the Earth times the gravitational pull from the block?
Careful. You're on the right track. The objects are block 2 and the Earth. The type of force is gravitational. That's what you need. So the idea is the Earth pulls down on block 2 using gravity. Therefore, block 2 pulls up on Earth using gravity. And it's the same size. You don't need to change the mass out. So, yeah, does that make sense? I don't know if you remember, I told you people miss this all the time. So I'll probably ask it all the time, and eventually you'll get used to it. So if the Earth pulls down on the block pulls up on the Earth, and they both use gravity. Why do we not notice it? The same size force on this block is really significant. If I use the same size force on the planet, it doesn't matter for anything. The planet could care less if there's this little block on it or if that block was in outer space. It's not really going to be affected by that tiny little weight force. All right. Good job. Jay, you had a chance to get some work there?
Yeah, I was able to pull up my my worksheet. So when I was
Okay.
doing it, this is actually the exact same problem that we were just doing. And so I like to draw my picture, like
Uh-huh.
triangular, my normal FBDs and my system FBD, and then my equations. So I write it very, very similar to that to you, how you do it, Professor Jorstad.
I gotcha. Would you say so? Is the workbook pretty good for this portion of the class?
Yes.
I think this is what I spent the most time when I first started writing. So use those solutions a lot and just try and mirror them as much as possible, and then you get kind of a system. All right. Hey, I appreciate that. All right. Hey, let's give Jay a round of applause. Yeah. There we go. Woohoo. Now that's coffee talking right there. All right. Now let's see. Let's try this. I am going to set up 2 breakout rooms. Jay, you go into the first one and I'll go into the second one. All right. And let me do this. We'll do 2 rooms. And the idea is I want you guys to work on problem 5.27. And I'm probably going to stop the live stream while we do this because I realize it's like the worst live stream ever to have me just going in and out of breakout rooms. So let me do this. I'll create the rooms. Okay. And then I'll open them. So Jay, you're in breakout room 1, and then I'll go into breakout room 2. And so go ahead and go in there, and just that way you could talk, and I'll give you guys a minute to get